So we will discuss the second distributed hash table algorithm called Chord. So a prerequisite of this lecture is the Pastry DHT, the Pastry distributed hash table. So this is a prerequisite of this current lecture. All right. So first we will discuss Pastry. So that has been done in a previous lecture. So now we will discuss Chord. So the lecture will go like this: overview, design of Chord, the basic structure, the algorithm to find the successor, node arrival and stabilization, and finally the results. So Chord versus Pastry. So the key idea is the same, that each node and each key's ID is hashed to a unique value. So this is same, but the process of lookup is different. So recall that in Pastry, the process of lookup tried to find the node that was closest to the key, but in this case we don't do that. What we do is instead that in the circle we try to find the node that is the immediate successor of the key. Alright. So we take the key's ID and we try to find the node that is the immediate successor when we are traversing the circle clockwise. The routing table at each node will contain roughly on an average order log n entries, and inserting and deleting nodes will require order log n square messages. It's just my view that this is more robust than Pastry and far more elegant as a solution, but that is just my view and you need not subscribe to it. So you make your own views by the time you reach the end of this lecture. So comparison a few of the other systems. So by the time that Chord actually came, there were many more DHTs in the research market. So there was the globe system, which used to assign objects to locations. It was hierarchical. As compared to that, Chord is completely distributed and decentralized. So of course, Chord also, similar to Pastry, uses a ring-based overlay. If you don't want to use it, you can use CAN. So CAN uses a d-dimensional coordinate space. So instead of a circle, it actually uses a d-dimensional coordinate space that's basically a hypercube, right? So a square, a cube, and a hypercube. So it's a d-dimensional coordinate space. If you don't know what's a hypercube, this is the right time for you to take a look, right? Just Wikipedia for it. So each node maintains order of d state, which is basically its d neighbors in the d-dimensional coordinate space. And the lookup cost is d times n to the power 1 by d. So it does maintain a lesser amount of space than Chord, but it has a higher lookup network. So CAN is one of the immediate competitors of Chord. And the interesting part is that as opposed to a circular overlay, which Pastry also uses, Chord also uses, CAN has more like this d-dimensional hyperspace. So this is a worthy competitor, but we'll still find the elegance of Chord to be something that will really endear it to us. So what are the features of Chord? Well, you have automatic load balancing. It is fully distributed. In terms of state per node, bandwidth and lookup time, it is fully scalable. Furthermore, there is great availability. It is always available in the sense that there is a built-in amount of redundancy into the Chord protocol. So that's the reason the availability is high. And second, it is provably correct. But the same was with Pastry also, that these are simple protocols. It's easy to prove that they actually work. Right? I mean, all corner cases are taken care of and they work in a robust, provable fashion. Design of Chord will take a look at the basic structure. So the key idea of Chord is called consistent hashing. So it is a hashing technique that adapts very well to actually resizing the hash table. So what is the key idea? It is that typically k by n elements need to be reshuffled across buckets. So what happens is, look, when you have a large space and you have these nodes, they are also called buckets, and you add a node in the middle, then you need to move some keys from here to here, right? So that needs to be done. So in Pastry it was a two-way move, but in Chord it's a one-way move. So this is again one more advantage. That is because we are storing the immediate successor, immediate clockwise successor, that is. So on an average, the number of nodes that need to be moved, and the same is for an add and for a delete as well. If later on we delete this, then some nodes have to be moved from here to here back. So the average movement is limited to k by n elements across the buckets, where k is the number of keys and n is the number of slots in a hash table. Number of slots in a hash table basically refers to the number of nodes in this case. So k by n is the typical movement, which is anyway on expected lines. It is not unexpected. And what we are basically seeing over here is that we will see how consistent hashing plays a role in Chord. Alright. So here, of course, in this figure we are using the term bucket. So we will get to it in some time. But essentially what this figure over here is showing is that on our big circular ring, different keys are hashed to different positions. And then we group them into buckets. So this basically means that a set of keys in one bucket are assigned to the same physical node. So I'm not showing the node over here, but if there is a node, then this entire bucket gets assigned over here because we assign them to the immediate clockwise successor. So the structure of Chord is like this. It's slightly different from Pastry. So each node and a key is assigned an m-bit identifier. So it's m bits. So we'll discuss what is the value of m. So the hash for the node and the key is generated using the SHA-1 algorithm. So it's a very simple hashing algorithm that takes the value of a node. The value of a node basically is essentially the IP address of the node. So given the node, we take its IP address, we pass it through an hashing algorithm, and this gives us the hash. And similarly, we take the key, we pass it through an hashing algorithm, and that gives us the hash. The nodes are arranged in a circle similar to Pastry. The major difference with respect to Pastry is that each key is assigned to the smallest node ID that is larger than it, or call it a clockwise successor. Alright, so that's the most important thing, that each key is assigned to the node that is just larger than it. So, basically it's clockwise successor. So the objective is that for a given key, efficiently locate its successor. So efficiently locate its successor on this ring, and efficiently manage the addition and deletion of nodes. So those are our two aims, to manage, to ensure that if we want, flexibility can be provided. And in this case, flexibility basically means that we can add as many nodes as we want, we can remove as many nodes as we want. So what is an advantage? I'll just quickly show it over here. So one advantage of this scheme is that, let's say we have the circular ring and we have some nodes, and let's say that it is the time of a festival. Let's say it's Christmas in the US, Diwali in India. That is when most of the shopping happens, and your favorite shopping site uses a DHT. Then what you can essentially do is that you can add more servers. So the new servers will basically be positions along this ring, and they can take away a large part of the load of the existing nodes, right? So the network will rebalance, and as we have seen, roughly k by n nodes need to be transferred between for adding every new server. So this allows us, this gives us a method to kind of flexibly expand, flexibly expand and grow the network, right? So let's say that when there is a festival, you expect a lot of people to be searching things, buying and selling things. So all of those things can be incorporated by adding extra servers in the network to share the load. And then when the festival is over, many of these new nodes that were added they can get deleted. Alright. So this is what gives DHTs the flexibility. Alright. So now let us see what are the properties of Chord's hashing algorithm, because pretty much the uniformity of the hashing algorithm to a large extent plays a rather important role in the design and operation of Chord. So for n nodes and k keys, as we have said, with high probability, each node stores at the most 1 plus epsilon times k by n keys. Addition and deletion of nodes leads to a reshuffling of order of k by n keys. So this is a property of the hashing algorithm of Chord, which is basically SHA-1. Previous papers have proven that epsilon is limited to order of log n, and there are techniques to reduce epsilon if we are really interested about the uniformity of distributing keys to nodes, using what are called virtual nodes. So what we can do is that we can make each physical node contain log n virtual nodes. Okay. So then if each physical node contains log n virtual nodes, so a virtual node, by the way, is a full-fledged node insofar as the hashing is concerned. So let's say that we have a ring like this, and let's say we have a physical node P, then the physical node P, if let's say we are creating log n virtual nodes out of it, then each node's ID will basically be the ID, the IP address of P with the virtual node number. So this will hash to, let's say, one point on the ring, the other virtual node will hash to another point on the ring, this one will hash to this point on the ring. Similarly, if there is another physical node P with, let's say, 3 virtual nodes, so one virtual node might hash over here, one might hash over here. So what this would do is that this would further increase the spread and the randomness. Think about it that way, that this will further, the number one, it will increase the number of nodes, so it's not a one-way street. So this will increase the load on the network, and it will just, in a sense, create a larger network. Alright. But also it will increase the amount of randomness and the spread. So the benefit will be that the number of keys that are actually stored on a physical node, it is expected to be substantially more uniform and more homogeneous in comparison with other nodes, which is what we wanted, right? Of course, there are scalability issues because we are increasing the number of nodes substantially log n times, so that is an issue. But if we want uniformity, this is a good strategy, because as you can see from the figure, if we have, let's say, 3 virtual nodes, they can hash all over the place. If this has 3 virtual nodes, it can hash all over the place. So given the law of large numbers, we can say that, look, the probability that the number of keys that will be there with each node, it's a very, very high likelihood that it will be k by n, where k is the total number of keys and n is the number of physical nodes, let's say. Then the number of keys will be k by n, or very close to k by n with P, if we follow this virtual node based scheme. And the reason should be clear from this diagram. So now let's see. So let m be the number of bits in an ID. So m is the number of bits in, let's say, both the node ID and the key ID, which is produced by the SHA-1 process. And for a node, whether it's a physical node or virtual node, as far as the lookup is concerned, it doesn't matter. It is only when we are looking at the uniform distribution of keys to a node does it actually matter. So we'll now define two terms, the successor and the predecessor. The successor is the next node on the identifier circle. The predecessor is the previous node on the identifier circle. So here is the fun part that we are going to do. We are going to define the notion of fingers, right? So if you see what is actually a chord, right? So a chord basically is that if we take a circle and we cut it like this, So this is a chord. So now it will be very clear why we call the system chord. So you take any point, right? Whether it's a node or a key, that is immaterial. So maybe let's start with a key. So let's, for every key, we'll have a position on the ring. Then what we can do is that we can, so the biggest chord of course will be the diameter, right? And then we can start defining smaller chords where we kind of half the angle every time, something like this, right? So as you can see, these are smaller and smaller and smaller portions of the circle, which they kind of gradually get bigger and bigger. So this is actually the way that we divide the entire space of keys by drawing a set of straight lines. And as you can see, they are chords. And the final one is of course half the circle. It's kind of the semicircle, right? So how do we do it? Well, let's first start by mathematically defining it. So for each of these, we call it a finger. So let's say these individual chords, right? So let's say something like this. We actually define this because as a finger. Well, it looks more like a pizza slice, but let's call this a finger. Okay. It also looks like a fingernail if you look at it from a certain angle, but I would have called it a pizza slice. So the ith finger basically contains, so every finger has a start and an end, right? So it has a starting point and it has an ending point. So the start for the ith finger, its position is like this: n plus 2 raised to power I minus 1 mod 2 to the power m. So why mod? That is because you want to wrap around the circle, you want to wrap around and come to the other side. So let's, and then the finger ends at n plus 2 raised to power I minus 1. So it's essentially you're increasing the size of the finger by a power of 2, which is something that you saw. So let me maybe show it to you in a table graphically, so that will give you an idea of what exactly I am referring to. So let's say that, let's say you consider I to be 1. So then what is the start? So let's say the ID over here, as we have seen over here, let this be n, okay? So n is the position. So I'm slightly changing the definition of n here. So previously n was referring to the total number of nodes, but now let this be the position of the key on the ring. So then this will be n plus 2 raised to power I minus 1, which is 2 raised to power 0, n plus 1. This is the start. And the n will be n plus 2 raised to power I minus 1, which is 2 to the power 1 minus 1, which is n plus 1. So then if I is equal to 2, then this will start at n plus 2, right? 2 raised to power 2 minus 1 to n plus 3. If I is equal to 3, this will be n plus 4 to n plus 7. Similarly, I equal to 4, this will be n plus 8 to n plus 15. So as you can see, we are gradually doubling the number of nodes in each finger. So they are getting bigger and bigger, ultimately till it encompasses half, right? So as you can see, this diagram is embodied in this math. So then for a general I, this will be n plus 2 raised to the power I minus 1 to n plus 2 raised to the power I minus 1. Alright. So the first finger is small, then slightly bigger, big, till it reaches the semicircle. So the first question is, why do we define fingers like this? Well, we'll see there's a massive advantage, but we'll gradually appreciate it. But I hope that the idea of these fingers is clear. The way that we define these fingers, and each one of them we are essentially drawing a line. So that's also why this scheme is called chord, because there is a circle, and any time 2 points on a circle are joined by a line, it becomes a chord. So finger I dot node. So for every finger we have a start and an end, which are only 2 positions. But finger I dot node is the name of a node ID, which is the successor, the clockwise successor of the finger I start. Alright, so it's the clockwise successor of start. So what is the basic operation? The basic operation is that for a given key, you find the successor, you find the node ID, that is its successor, which means that from the key we start walking the circle clockwise until we find the node, that is until we find the nearest node, and that nearest node is the successor. Alright, so what is the algorithm to find the successor? This is by far the most important algorithm in Chord. So we should take a look at this pretty seriously. So again, just to come back, if I were to look at a circle and give actual values, so then what we would see is for the node 3, and for the 3 fingers whose start is 3 plus 1, 3 plus 2 and 3 plus 4, their successor or the node of the fingers is node 8. But for 3 plus 8, which is the next finger, there is already a node over there, so its successor is 11. And if let's say there is a key that arrives, the successor of key whose ID is 14 will be 15. And 3 plus 16 is the next finger, its successor would be node 22. And 3 plus 32's next successor will be node 40. So of course this diagram has not been drawn to scale, it is meant to show you certain things. But of course it's not fully drawn to scale, so don't expect a semicircle when you are not finding one. It's just an illustrative example. Let us now discuss the algorithm to find the successor. So the key idea over here is that if I have the ring and I have an ID over here, I want to find the successor node of this ID, the one that this ID is mapped to. This can be the ID of a key or it can be the ID of a node. So it doesn't matter at this particular point of time what it actually is. Alright. So what we do is that we contact one of the nodes that we already know, which is node n, which is a part of the ring. And then we ask it to find the successor of ID. So we call the function over here n.findSuccessor ID. Alright. So what we do is that it turns out that to find the successor over here, it is actually easier to find the predecessor. And since every node has a pointer to its successor, we arrive at the predecessor first and then from there we arrive at the successor. And this node will also be the successor of ID. So this is exactly what we do. We initialize node n dash, which is the predecessor of ID. From n dash, we find the successor of n dash, which is what we need to return. So to find the predecessor, what we do is we follow a recursive procedure. So I will show this in a slightly bigger diagram. So consider this to be the ring and consider this to be the starting position and this to be ID. So what we do is we find that finger of n, which we am calling the closest preceding finger, whose finger node, so recall that the finger i's node is basically the successor of finger I.start. Alright, so finger i's node is the successor of finger I.start. So we find that finger of n whose finger node is the closest preceding, in the sense that if let's say I start here and I walk anti-clockwise, so I'll encounter many finger nodes of node n, but I want the closest one, the first one that I encounter while walking anti-clockwise. So it is possible that there could be a finger of this type. So this could be the start of the finger. So sorry, this is the start of the finger. I stand corrected. This is the end of the finger. And maybe the node of the finger is over here. So this is the finger's node. Alright. So let's call it the finger node. So from here I can immediately reach here, which is the best information that I have about ID, right? So I can look through all my finger nodes and find the closest preceding one, which means that out of all my finger nodes, this is the one that is closest to it and precedes it. So this I can do very easily. I just need to search within my finger table. Node n needs to do that. Let us now blow this thing up. Okay, let's have a magnifying glass and let's blow it up. So let's go to the next slide. See, if I blow it up and then I look at it, so it's possible that ID is over here and then the closest preceding finger, which I'll again call node n, or let me call it node n dash, is here. So again this will have a bunch of fingers, right? So one among those will be the closest preceding finger node. So let us say that n dash will again do the same. It will again find this point, which is the finger node of the closest preceding finger. So the way that we have defined it. Again what we can do is we can blow this up and again we can look at this. Again we'll have an ID over here. Again we'll have a point n dash over here. We can again look at its fingers and again come to a node which is even closer, and this is the closest preceding finger of ID as per n dash's information. So if this is n dash, let's call it n double dash. Again I can start from this point which is n triple dash and keep on narrowing myself, right? Narrowing and narrowing and narrowing until I reach a point when ID is between whatever node I am considering and the successor of the node, right? So until ID is between these 2 points, I'll keep doing, and I'm ultimately, given the fact that I'm continuously reducing the distance to ID, I'm ultimately guaranteed to find such a point. So at this point, I actually stop. So this point tells me that I have found my position. So at this point I actually stop. So exactly what we see in code is something very similar, where what we do is that we initialize n dash to n as long as our condition is not met. Which one? The one that I showed just now, that ID is not between n dash and n dash's successor. I keep on finding the closest preceding finger, keep on setting that to n dash, and I keep on repeating in a recursive fashion. So I just keep getting closer and closer. So maybe this is his closest preceding finger. Again I get closer, closer, closer and closer. Ultimately this condition will hold, and that's when I know that I am done. So I'll return the value of n dash, which is the predecessor, and the predecessor successor is what I am after. So now what I need to do is I need to figure out how the closest preceding finger function is written. So the way that this is written is again rather interesting. So again I need to draw a big fat diagram to explain. So if I were to consider this as the relevant part of the ring, or maybe I can show you the entire ring. Okay, of course this is not drawn to scale. So this point is node n and this point is ID. So what I do is I start walking backwards from the biggest finger to the smallest finger. So this could be the biggest finger. So from here I start walking backwards, alright. So let's say that if let's say this is the mth finger, so then of course this is the starting point of the finger. So then the finger node will be after that. So I'm not after this. So maybe let's say that this is the m minus 1th finger. Okay. And so then I will start at, this is the starting point. Again, I will see if there is a finger node, if the node of this finger is before ID. If it is, then I will return that. Otherwise, I'll look at the starting point of the m minus 2th finger and also look at the finger node. So if the finger node is between n and ID, then I will return that. So that is the way that I will proceed. The reason that I proceed this way, anti-clockwise and not clockwise, is basically because I can kind of eliminate most of the circle by considering the largest finger. Then I can eliminate most of it by considering the second largest, so on and so forth. And furthermore, the first time I find a match, which means so what is the match? The match is that if, let's say, the match is for the ith finger, it means that the node of the ith finger is in between n and ID. If it is in between them, the first time I find such a match, which means the first time I find that, look, this node is over here in between n and ID, I can simply return that as the result of my function. So this is what I am doing in the code, that I am starting from the largest finger and counting down to the smallest. Any time that my function holds, which means that finger I dot node, the node of finger I, is in between n and ID, the first time that it holds, I return finger I dot node. I'm done. So there is a possibility that I will not find a finger I dot node that satisfies this condition. When would that happen? If, let's say, n and ID are close by. So none of its fingers, the successor of the start, are actually between this range. Then it's easy. Then it means that the current node n is the closest preceding finger. So that's like the trivial case, and n can simply be returned. So this is a very important operation, so I would request you to kindly go over this part of the video several times until you understand all of it, and particularly the special case which indicates that the starting nodes that the finger nodes, all the finger nodes are after ID. So every finger, recall, this is a very important concept, don't forget, has a start, has an end, so that's the range of the finger. But the most important thing that we are concerned about is the successor of start, which is node. And if you are unlucky, the finger node can be after end also, because there might not be any nodes within this range. So this is an important thing that we need to bear in mind. Now here is the fun part. Alright, so the fun part is that what is the complexity, right? So when you are talking about the complexity of this algorithm, we really don't care about the number of operations we perform within each node, because that is assumed to be extremely fast in any distributed algorithm. The only thing that we care about is how many messages are sent, and that too sequentially. So that's the only thing, right? So we don't care about what a node is doing. That's assumed to be infinitely fast. So if that is the case, over here, we need to understand how many messages are actually sent. So let us look at this concrete example over here. So consider this example of a set of nodes, and we are interested in ID number 17. So this can be the ID of a key, ID of a node, it doesn't matter, right? It's not that important. But here is the important part. The important part over here is that this is lying in the ith finger. Alright. So why do I say that? Because 3 plus 2 raised to power I minus 1 is basically 11. There is a node over there. So this is its finger node. And 3 plus 2 raised to power I minus 1. So in this case, what's the value of I? Well, it's I is equal to 4. So 3 plus 16 is 19. And clearly the finger node of the next finger, I plus 1th finger, is 22. So as far as 3 is concerned, the closest preceding finger of 17 is node number 11. Alright. So this is how we are going to proceed. This is an example. So given that that is the case, can we derive some sort of a routing complexity? For that, I'll again take you back to my big board. So where we'll draw a big circle. So I drew a circle as big as I can. So here is the point. So let's say I'm starting at n, and this is where ID is. So in my estimate, on an average, right? So we expect that our nodes are equally uniformly distributed, homogeneously distributed across the ring. It's a massive ring, and I'm using consistent hashing with a very random and uniform hashing function. So I can say that, with a good certainty that overall my nodes are uniformly distributed, right? So now let's say that between n and id, I expect k nodes to be there. Then I find the closest preceding finger, and let's say the closest preceding finger is at this point, and this lies within the ith finger. Alright. So now the key point is that after this I will start my search from this point. How many nodes are expected to be between this new point, let's call it n dash, and id? Right? How is this related to k? That's the most important question. So the distance between n and n dash, if I were to measure it in just in the id space, not in terms of the number of real nodes, the distance between n and n dash will at least be 2 raised to the power I minus 1, given the fact that it is within the ith finger. Furthermore, between n dash and id, so it's in the ith finger, it's not in the I plus 1th. So here there is a little bit of a complication, but let's consider the simple case first. So let's consider that the I plus 1th finger will start from here. Then you can clearly see that this distance is much more than this distance. So I can say that the distance n to n dash is more than the distance from n dash to id. So this is just the key distance. This is just the distance in the id space. So you can clearly see, because if that was not the case, then the closest preceding finger would not have been the ith finger, it would have been the I plus 1th finger. Of course, there is a little bit of a complication over here, which I'll discuss later. But here again, I'm considering the simple case where within the ith finger we are finding it. So if that is the case, we can clearly see that the distance from n dash to id, right, measured again in the key space, is going to be less than the full distance, which is the distance from n to the next finger, which is 2 raised to the power I. Alright. So what is this? So the main idea is that the distance from n to n dash is greater than or equal to 2 raised to the power I minus 1, and the distance from n dash to the beginning of the next finger, and assuming that id is before that, this is bound to be less than 2 raised to the power I minus 1. So I can write it over here. I mean, assuming that things are in control, right? So I'll discuss when they will get out of control, not now. So if that is the case, if this is the simple case, then what I can say is that in the ith finger, if let's say I was considering a span of 2 raised to the power I entries with n, then when I start from n dash, I'll actually be considering a span of, because n to id, what was the maximum distance? It was 2 raised to the power I minus 1 plus 2 raised to the power I minus 1, which is 2 raised to the power I. Now when I start from n dash, I'll be considering a smaller span in the key space, which is 2 raised to the power I minus 1, which in other words is 2 raised to the power I by 2. So with every closest finger operation, my span, the area in the key space that I'm looking at, that is reducing, that is dropping by a factor of 2. But again, this is the key space, okay? So now there is a little bit of a problem. It is very well possible that instead of this point, right? So let's say that this is where the I plus 1th finger begins, and my ID is over here. Why is ID over here? Because it's possible that the finger node of I plus 1 lies over here. I plus 1 dot node lies over here. So then what will happen is this logic will not hold, but we also realize that there is no node bit in this region. Had there been a node in this region, finger I plus 1 dot node would not have been here at the top. It would have been between the start of finger I plus 1 and ID. Alright, but that has not happened. Given the fact that this has not happened, we are in a far better shape. So what we can say is that look, this part is empty. So as far as we are concerned, the distance from n dash to ID, if I were to just count the nodes, I can ignore this part because I'm sure that there is no node over here because of the logic that I just gave. So I can still say that if I were to break this in expected number of nodes, so if let's say that, let me define a new distance metric, which is the number of nodes that lie between n and n dash, expected number. So let's call this, let's say dn. Between n and n dash will be some function of, some linear function of 2 raised to the power I minus 1, right? We can also say that the distance in terms of the number of nodes between n dash and id is also expected to be some linear function of a number, of some number which is basically, let's say, of some number x, which will not really be the distance between n dash and id in the key space, because we know that a large part of it is devoid of nodes. So it will actually be some function of x, where x is basically this distance, which is less than 2 raised to the power I minus 1. So using the same logic, regardless of where it is placed, we can say that even if we were to measure the distance in terms of number of nodes, and the number of nodes in a given region is proportional to the size of the region in the key space, using that logic we can say that look, if there were k nodes between n and id, between n dash and id we expect that there will be less than equal to k by 2 nodes. And the reason that I say that is because we are roughly halving the distance. If it is lying within the ith finger, even if it's lying outside the ith finger, regardless of where it is lying, from the end of the ith finger till wherever id is, there are no nodes. So as far as we are concerned, we are primarily still, the unknown region is limited to, the unknown region as such is limited to between, the old, wherever id is, so the unknown region is limited to this starting of the next finger and n dash, alright, so which is less than the other region. So we can say that this is less than equal to k by 2. So every iteration of closest preceding finger, we are reducing the search space of nodes by a factor of 2. So this will immediately tell us that look, if we just keep on dividing it by 2, ultimately log n to the base 2 searches have to be done in terms of closest preceding fingers. And this is the number of messages we'll have to send over the network till we ultimately find the predecessor and consequently the successor. So coming back to our presentation over here, the log n logic is clear to us. So it's not given that clearly in the paper, but you will have to consider all the sub cases and corner cases that I discussed. With that, it's very easy to see that it will be order log n. And we also see this coming out experimentally as well. Now node arrival and stabilization. So each node will maintain a predecessor pointer. It will initialize the predecessor and the fingers of the new node. It will update the predecessor and fingers of other nodes. And then it will notify the software that the node is ready. So in most implementations of Chord, we have a successor pointer as well as a predecessor pointer. So we know which node is there on both sides, right? The successive node and the preceding and the immediately preceding node on the ring. All right. So how does a node arrive? So let's say that this is the node n and it wants to join the ring. So initially it will contact one of the nodes that is already a part of the ring, right? So this will be, let's say, node n dash, which we know already that it is a part of the ring. So then it will join. So it will ask n dash to initialize its finger table. So there are two basic options, basic operations. The first is that for the node that is joining, its finger table needs to be initialized. Second, others have to be updated. Alright, so we need to update others. It means the finger tables of other nodes, saying that they need to point to me. So the init finger table, this is how it works. So n dot init finger table n dash. So let us consider the node for the first finger 1 dot node. So we will ask the node n dash to find the successor of finger 1 dot start. So that is pretty easy, right? So we'll just ask node n dash that you kindly initiate an algorithm and find the successor of my start, and that is done. So that becomes my successor. So finger 1 dot node, as I said, every node maintains a pointer to its successor. So once the node n dash has done this basic service and it has found the successor for the first finger, that is also the successor of the current node. Alright? And that can be stored in the successor's pointer. Furthermore, the predecessor is actually the successor's predecessor. So what we can do is we can ask the successor node, look, who's your predecessor, and we can initialize that. Then we need to do a little bit more of math. So we need to also record that the successor's predecessor is the current node n, and this will require a message. We need to tell the successor that, look, I am your predecessor, and we need to tell the predecessor node that, look, I am your successor. So predecessor dot successor is the current node n. So this is no rocket science. It is similar to inserting a node in a doubly linked list. Okay, so this is no rocket science. Then what we need to do is we need to look at the fingers. So for I from 1 to m minus 1, here is what we do for all the fingers. So we look at the I plus 1th finger. So if finger I plus 1 dot start, okay, so if let's say for the current node whose node is being initialized, if the start of its I plus 1th finger is between n and finger I dot node. So what does this mean? That I am node n. This is my finger I dot node. So let's just call it maybe finger I dot node, right? And let's say finger I plus 1 dot start is over here. It is starting over here. Then it's very easy to see that finger I plus 1's node will also be the same node, because from here if we start walking down the ring clockwise, the first node we will encounter is finger I dot node, which is its successor. So we can say that finger I plus 1 dot node is finger I dot node. Alright, so this should be obvious. If this is not obvious, it means that the way that these fingers and finger nodes are created, that is not clear to you. See, if let's say you are not able to understand line number 4, the logic behind line number 4, the way that I explained, let me draw it again to make it slightly clearer. So this is finger I dot node. So as I said, if this is not clear to you, kindly don't proceed. So at this point, this should be absolutely clear to you why I am doing what I am doing. So I am saying if this is finger I plus 1 dot start, from here I'll just traverse the ring clockwise and I should arrive at finger I dot node, and that should be the first node. That should be my successor, because from finger I dot start, when I walked, this was the first node that I saw. So if this case is holding, this will also be the first node that I will see. But as I said, it's very important you understand this line before you actually proceed. Alright. So then, if this is not the case, if this case is not happening, then we'll again have to request node n dash to find the successor of finger I plus 1 dot start for us. Alright. So it needs to do the same again. It needs to again find the successor of this for us, and then we will use it to initialize. So we just keep on doing it. We just keep on doing it for the rest of the m minus 1 fingers. So this will initialize the finger table completely. So now once my own finger table has been fully initialized, what I need to do is I need to update the finger table of others. So what I do is I take a look at all the m fingers. For the ith finger, we find the predecessor of n minus 2 raised to power I minus 1, which means that if this is my current ID, I just subtract 2 raised to power I minus 1, which means that I will lie in the ith finger of somewhere. So for this point, I find the predecessor, which is maybe this node. So for this node, I am going to be the ith finger. So I'll go to this node pred, and I'll send a message and I'll pretty much say that, look, I am now your ith fingers node. So you kindly update your finger table and say that, look, node n is the node for I. So what I would do over here is that I will call the update finger table function over here, which you see here at the bottom. So I'll do it for all my fingers, and each time I'll call the update finger table function. So when I am doing that, here is a check that I'm going to do. It's a very important check. If let's say for node between pred, so for its ith finger, it will have a node, right? It will have finger I dot node. And let's say the current node n lies somewhere here. If it doesn't lie, I'm not interested. But let's say it lies somewhere there. Then the current node n will be set as the ith finger node for pred. That's point number 1. Furthermore, there might be a need to cascade this information. So it will look at its predecessor. It will then send a message to its predecessor that, look, I have gotten information that node n has been added. Node n sent me a message. I found the message to have merit in it. So I added node n, which was lying between me and my previous finger I dot node. So I added it as the finger node for my ith finger. It might be a finger node for you as well. So why don't you also kindly check? And if that is the case, then you also update yourself. Alright. So then it will keep on cascading this to its predecessors until all of them update. So this procedure is done for all the fingers. So by this we basically ensure, so mind you, we only walk in a certain direction which is anti-clockwise, because that is the way that we created our finger table. So once the rest of the nodes have updated their finger table, the process of node addition is done. So then we'll do a little bit of node stabilization. So the node stabilization is required, particularly if you have race conditions and so on. So what I will do is I'll look at my successor's predecessor. So I'll look at, if this is the node, I'll look at my successor's predecessor. It can be the previous predecessor or it can be me. So if let's say that my successor's predecessor, so this is essentially looking at this. This is me, this is my successor, and this could be my successor's predecessor. If that is the case and this node x is between n and the successor, then the successor will be made x. So this is one way of periodically fixing the thing. So I check that am I my successor's predecessor? If I am not, then is there a new node x that lies between me and my successor, right? If it lies and still, the network is in a position of getting updated, because as I said, it's a race condition. If that is the case, I'll simply set x to be my successor and I'm done. And furthermore, I'll notify the successor, the new successor, that look, I am your predecessor. So this notify function will be called. And if in the notify function, if there is no predecessor, or the node that is claiming to be the predecessor is actually the predecessor because it lies between me and my previous predecessor, then I set predecessor to n dash. So both these operations are what are called stabilization operations. So they help to fix any temporary inconsistencies in the network. So those issues get fixed. So then also we can fix the fingers. So let us say that some error has cropped up somewhere, and because of that there's a little bit of inconsistency in the bookkeeping information that is there all over the network. What I can do is I can fix fingers, which means that at random, if let's say I is a random number, at random, I should have a semicolon over here. So finger I dot node, the node of the ith finger, I can set it to find the successor of finger I dot start. So this should hold anyway, but because, as I said, because of some temporary inconsistencies that may crop up, this may not be holding. So this is where there is a need to periodically run this script and keep on fixing the network. So now we will discuss a thing or two about the evaluation setup. So the network here consisted of 10,000 nodes, and the keys varied from 100,000 to a million. And the experiment was repeated 20 times. So you can also see error bars in the figure. And they didn't actually do it on a real data center, on a real distributed system. This experiment was done on a simulated environment. So what we see is that the number of keys per node decreases with the number of virtual nodes. And also, why did we add virtual nodes? Well, we added virtual nodes for better homogenization and to ensure that no node becomes a hotspot. So for one virtual node, we could have up till 500 keys per node with a mean of 100. And for 10 virtual nodes, we can have roughly 50 to 200 keys per node. So what you can clearly see over here is that if you have less virtual nodes per physical node, then the lack of uniformity is large, right? So from 100 it is going till 500. So there is a lack of uniformity. But if I have 10 virtual nodes per physical node, the way that we have been arguing, you can see that we will only have the uniformity is more, or let's say the load is kind of equally balanced across the physical nodes, right? So go back to the slide where we discussed virtual nodes. So here we have roughly 50 to 200 keys per node. So kindly hang on to this concept of virtual nodes, is very important. So this will be used in the third part of the chapter when we will discuss commercial networks, because they also use virtual nodes for exactly the same reason. So this is used as a load balancing technique, as a load balancing trick, to ensure that even if we are using the best hashing algorithm, it will happen in real life that some nodes a lot of keys will be mapped to it, and for some nodes very few keys will be mapped to it. So as you can see, you'll see a higher spread. If you want to reduce that, have more virtual nodes per physical node, that will solve this problem to a large extent, as you are seeing over here. So the path length in Chord grows with the number of nodes. So if you see the paper, it will show that it is roughly normally distributed about the mean. So for a mean of 6 nodes, so mind you, for a similar network, the path length in Pastry was much lower. The path length in Chord is slightly more. So the plus or minus 3 sigma range is approximately, if you look at the mean, the plus or minus 3 sigma range does vary from 1 to 11, and the corresponding variance in Pastry was slightly lower. But as you can see, it increases in a nice log n kind of fashion. So it's around 2 for a 10 node network, 3 for a 100 node, 4.3 for 1000, and 6.2 for 10,000. And so in that sense, it is scalable, even though the overheads are slightly more than Pastry. So there are other DHT systems. It is just not Pastry and Chord. So for example, you have Tapestry that uses a 160-bit block ID. So it should be 160-bit block ID with octal digits. So the routing is like Pastry. It is a digit-based hypercube. So it doesn't have a leaf set or neighborhood table. And also, it is not necessary that all designs will have a ring-based overlay like Chord and Pastry. So in this case, it is a hypercube. So it has a different kind of an overlay. So Kademlia is the basis of BitTorrent. So each node has a 128-bit ID where each digit contains only 1 bit. So Kademlia will be the next lecture in this lecture series. And we find the closest node to a key. So there is some amount of reliability in the network in the sense values are stored at several nodes, and nodes can also cache the values of popular keys. So that is also doable. So we will discuss BitTorrent next. And one of the most influential proposals in this area is CAN, content addressable network. So we have discussed this earlier also, where we use a d-dimensional multi-torus as the overlay network. So recall that a torus is basically a network. It's a mesh with the corners connected. So we have long connections of this type. So this is of course 2-dimensional. We can have the same thing in 3D. We can have the same thing in n dimensions. So it uses standard routing algorithms for tori. Tori is the plural of a torus and uses a virtual coordinate zone. So whenever a node arrives, we split a zone, and when a node departs, we merge a zone. So essentially we break this into zones, and that's how we do the routing. But the CAN paper is available online. So I would request viewers of this video to take a look at the CAN paper as well. So these were the most popular DHTs. So we started with Pastry, Chord. So we will have a short 15-minute video after this to discuss BitTorrent and Kademlia. And that will heavily build on whatever has been taught in the past 2 lectures on Pastry and Chord. So of course Tapestry and CAN and Kademlia are all there. And there are some new papers. So I'll just maybe write it down. There's something called Fawn, which is for extremely small nodes based on USB sticks. But BitTorrent is clearly the most popular as of today when it comes to openly available networks. And almost all major companies like LinkedIn, Amazon, Facebook, etc., they have their internal DHTs which store data, right? So they, of course, instead of a login time access, they have a one-hop access. So we will discuss them in the third part of this course. So this was the Chord paper. And so the next lecture will be on BitTorrent, but it will be very brief.